forward. Let me just share my screen. Okay, so okay, so hope you are all able to see my screen.
Yes.
Okay, so
Yes, sir.
this was a comparator circuit that we did, and we
Yes.
discussed about this peak at positive edge only, why it is there. So that is clear. Now we will move on to our next part. Let me just uh, delete this. Okay, so the basic thing is this only. The next circuit that we are going to do is an
So
integrated. Yeah,
sometime
tell me
as it's shown that the out of date that the information what will actually indicate
how to update
out
what?
of out of date like as we are on the screen out of date like that. Sometime this information will come.
Okay, okay. This will happen, sir, when let's say let me just show you how why it is happening. Okay, so let me just connect it this to ground. Okay, now if I run this circuit, okay, so the circuit is running and I have some sort of data here which is coming. The graphs are also here, perfectly fine. So now I stop it. Okay, so these probes here, so graphs is not required here. So these probe here is showing the value that was last read by this particular probe. Okay, so this is what it will keep on showing. But let's say now if I make a change in the circuit, so now you know that that previous data which was there, it that data was for the circuit which we earlier had. Now we
Oh,
have done some changes. Okay,
okay,
so that
okay, sir,
change,
I understand.
that is why it is showing out of date, because this data does not hold correct now.
Okay,
Because
sir.
now if I run the circuit, it would be something else that we will get. Okay, so now again let's say if I stop, so it is showing you the last value that it has. And now let's say if I connect it again, oh, sorry, let me connect it here. So again it will show out of date, out of
Okay,
date. This reason is because the circuit has been changed and this data is not correct now. Okay,
okay, sir.
so that is why it was showing that.
Okay, sir.
Okay, so
Oh,
okay, any further doubts? Okay, so we will look at the integrator circuit. This circuit is again a simple one. You see, we just need one resistance and a capacitor here. Okay, so resistance we already have, and we just need a capacitor. Okay, which will be connected between output and input. So it would be a feedback capacitor. Let me just connect it. 1 second. Okay. Okay. Now let me just take this here, delete this wire, and put it here. Okay, so again this will be rotated. I'm just aligning things right now, so just give me a minute. Then this one here. Okay. Okay, so this is what we have. Now we just need our Okay, so we will need one resistance which will go here. Okay, and now we will need one capacitor which will be a feedback capacitor. Okay, and this would be again grounded. No, I guess that is it. Let me just run the circuit. Okay, so we know that we have given a sine wave. What we should be getting, one second. Okay, one second. Let me just change the input source from sine to something else. Let's say clock. So what would be the integration of this?
Triangular waveform.
Yes, so we should expect a triangular waveform now. Okay, so let us just run it. We are not getting that. Maybe some values we need to change. No changes at all. So we are getting a square wave only actually. This actually is a square wave only that we are getting, but at a very small square wave. Let us just run AC sweep first. Okay, so it's displayed using a linear scale. So has been removed. Can be only displayed on the linear scale. Mhm. So are we missing anything here? Can anyone tell what can be the issue?
So integration should be spikes. Integration of square wave.
So no, that should be here now. At this place, input should be a square spikes. That is what you're saying. So let
No,
us just put.
input is square wave, output is spike.
Okay. So okay, so this is triangular wave
This
we are
is
getting.
correct, sir. This blue one.
Okay, okay, okay. So this
Spikes we
blue
will
is
get
the,
only for
sorry.
differentiator only. We will get spikes. This integrator, so we will get the triangular waveform. Now it
Yes,
is.
sir. Spikes
Now
is
it's.
in differentiator.
Okay, sir. Now it's. I think now it's okay.
No.
Okay. So okay, so we are getting triangle wave here. Okay. So actually, the integration part is done by this part. This
Capacitor RC.
capacitance and the resistance. This is what will do the
RC.
integration part.
I think by changing the resistance value, we can get the amplitude some high amplitude for triangle wave.
If
And
we change what, sir?
you can train the R value, resistance value R1.
Yes.
I think by changing that, we can able to get some
That
voltage.
is what we are getting.
Yes.
This is 0 right now, so let me just give it some particular value. Okay, so let's say we give 270, or let's say if we increase this
Or we can change capacitor value. Can either
capacitor,
change or C by.
it is inversely proportional here. Actually, what we are getting here, just one second, we are getting some DC also on the output. So let me
Or
put,
even we can change the frequency of the input waveform. So we
yes, sir,
can change
that also we can try.
and that also we can.
See, now we are getting three waves here. One is the original signal. Second is what input we are giving here on the op-amp, which will be amplified. Then the next one would be the output. This capacitor is basically we were getting some DC here because the output wave was somewhere around this -10 line. So I've added this so that it is all in the same origin. So decrease that DC, I just added this. So let us just see what we are getting now. Okay, so first thing first, let us see our input. Sorry, not this is our input. This is our input, a square wave, what we are sending. Okay, then what we are giving to this op amp. Okay, then this is what we are getting, spikes. Someone was saying that it should be spikes at the output.
Sir, spikes we get it in differentiator circuit.
Okay,
And in integrator circuit we get triangular wave.
you get triangle only.
Yeah.
Okay, so
Can we just can we
any
just check? Can you just check this circuit with some other in Google search also?
yeah, that we can do. But any particular reason why we are getting this right now? Any particular reasons why we are getting this?
Spike.
So I think we can remove the capacitor C2.
Due
Yeah,
to resistor capacitor due to resistor capacitor combination
this one.
capacitor की वजह से शायद सर.
Okay, so
Such
if I
external this C2 capacitor,
Yeah.
okay, so you're saying C2 is the issue. So let's
we
delete
can
C2.
remove this.
Okay, now let us see what we are getting. So this is a square wave here. Why we are getting square now?
The light blue one is our output, sir. Light
Yes.
blue color. This is input.
This is our input.
This
The
is
third
input. This is purple is what we are giving to at op
Okay.
amp.
So we don't
Out.
see our
so,
this
We
here.
don't see any output.
Here again we have spikes only.
Spikes. Only.
So that actually I tell you that capacitor I added because right now you can see that it is at -12 level. So there is obviously some -12 DC offset here, which is because of this part only. Okay, so that is what I just to remove that part I added that particular capacitor. That capacitor has no effect here. Okay, because our feedback is anyway taken before that only. So now if you see our spike is also in the same scale. So for that only I was just adding this capacitor. This capacitor has no effect here. Okay, so let me just okay, so this is what our output is, and this is what we are expecting to be like this should be triangular as per the
yes.
uh, circuit what we know, but still we are not getting that triangle. Any particular reasons? You see we have square now here. This is turned into square.
Sir, if we swap this R1 C1, then it will be differentiator. So
Yes.
then spike
So
should be
let us
there.
just try that. Let us try that also. Okay, so let me delete 1 second. Okay, then this also we should delete. This we will delete. So capacitor will come here. and the resistance will go here. And this one will be connected here. This will be connected here and here. Okay, and our probe obviously one is here. What output? Sorry, not here. And then this one is here. So now if I run it, okay, let me just okay, so we are getting this now. See, now we are getting triangle.
But sir, integrator should give triangle and differentiator should give spike.
Yes,
It
ma'am.
is reverse.
This is some, maybe we are missing something again, or what? Because there's definitely something we are missing here.
Yes.
Yes, sir, it is now somewhat different, sir. Because it's integrator
So
circuit. First,
what?
what
Uh,
the circuit what we done is first is correct, sir.
No, I didn't get it, sir. What?
The circuit what we drawn first is actually correct. You check the book. So if
This one is
integrator first we have capacitor to be replaced by resistor and
no, no.
circuit what we drawn previously is correct. That is what you.
so just check the circuit with. Yes, yes. On Google also.
What you show is correct. I will check that first we have
Yeah.
a
So
resistor and
this is what
capacitor.
we should be having.
Mm.
Okay, so this is our circuit. So first resistance, then capacitor. Even if we want, we can
Yes.
add another
One more rest. This
resistance.
was the circuit which I am having. तभी
Okay, so
मुझे लग
this basically
Okay.
is an integrator what we are having right now. So
Yes.
earlier one was the correct one. Let us just make that. So this we can do using Control Z here, undo part. So let me now what I'll do, I'll copy this and I'll put one in parallel also. Let us see what effect this will give. Okay, so now if I run it, now what we are getting. Okay, so now sort of spikes are what we are getting.
Still,
So if I change the frequency, sorry, if I change the frequency now, see what we get. Let's see if we get this particular thing. Okay, still not. We are still not getting that. Now, can anyone tell why we are not getting our output here? There should be some error. You see, input and output, whatever we are giving here and what we are getting is almost same. So that is okay.
Feedback capacitance.
What now?
C2
Feedback
capacitor.
capacitance.
C2 capacitance.
Yes. Feedback one is C1, sir. C1.
Okay, that is okay. So C2 I told you that I'm adding just to remove that extra DC what people getting. C2 doesn't have any effect. So let us run now. See? So this DC only I wanted to delete. See, we are getting spikes actually in the output. Okay, it actually is working as a differentiator. Why is that? What we are missing here? The circuit we are using is same. Ideal integrated differentiator. Okay, so okay, let me just change the input source back to a sine wave. Make it 15. This won't be an issue. This 100%. Okay, so what we are getting here is an inverted sine wave, which also should not be here.
I discussed that because it's a cos wave. You are integrating, it
What's
become
it?
cos. If you're integrating, it become cos.
Cos is 90-degree phase shift, na? You're
Yes,
getting 180-degree phase shift here, sir.
that's what I am thinking. 180 phase.
This is not.
Sir, this RC product can be changed.
This RC.
R1 and C1, sir.
Okay, so let
So
me.
by changing
R1
the
we can keep at 100 ohms and C at 1 microfarad.
Okay, let us just try it and
100 kilo
this
ohm.
100K.
100 kilo ohm or C1 at 1 microfarad.
C1 at 1 micro. Okay, so 1 micro. You see, we're getting a flat plus 15.
Hello, sir. Hello.
Yeah,
Sir, nothing, sir. Actually, you design for some frequency, sir. Like maybe 1 kilohertz or 10 kilohertz, like that.
that is what I'm saying. That these.
Ah, then
we can
assume
use
the
the
C,
formula 1.1 RC. We can
assume the C value, sir. For ideal integrator, I'm saying, okay.
for
Okay.
1.1 RC. We can use the formula.
F equal to 1 by 2 pi RC. By assuming the C value, you can able to get the R value, sir.
Yeah, let us just calculate that also.
Can I share, sir?
Yeah, if you want, you can share, sir. No problem. Where was it? Okay. Please share, sir.
Yes, yeah. So then for ideal, sir, I'm taking only one RC combination, okay. Ideal integrator for 1 kilohertz, sir.
Okay, now this is correct.
second, sir. I designed for 1 kilohertz, sir.
1.6, okay, 1 kilohertz.
I'm assuming that the corresponding capacitance value 0.1 microfarad.
Okay, and
So
1.6.
frequency is nothing but 1 over 2 pi RC.
Yeah, yeah, I know. We'll do
So
that
from
formula.
that I calculate the value of R is nothing but 1.6 kilo ohm.
Okay,
So I kept the frequency 1 kilohertz frequency, sir.
okay,
So here we're applying input at the inverting under. Here we're applying input at the inverting terminal, sir.
okay.
So
Minus,
integral of sine is nothing but minus cos.
yeah, cos.
So in addition to those things, we're applying at the inverting, so we're going to get only cosine thing. That's 90-degree phase shift is
Exactly,
happened over there,
exactly.
sir. Okay. Now just I'm run this thing.
One second. Okay.
The
So
corresponding
that
input,
anyway
sir.
is working fine. So
Green
let
color,
us,
sir. This blue
yeah,
color
I
is
know.
denotes that output. 90-degree
Yeah,
phase shift, sir.
that is okay. So there's a 90-degree phase shift you can see.
Yeah. Yes, sir.
Okay, so that also we have also done same. So
This
what?
regard ideal integration, not practical thing.
Yeah,
Ideal
yeah.
integration with one
So
RC
this is
combination.
an ideal thing, but
Yeah.
obviously in practical we don't get ideal effect.
Yeah. Fine. Just I would like
And
to convey.
let me just show my screen also. So now,
Yeah.
However,
Fine.
we can use this value, sir. However, we can use this value of R and C and then nano for
yeah,
in our circuit.
I just use this. I just used it. So let me
I
just
stop
show.
sharing. So okay.
Yeah, yeah. So my screen is visible now.
Yes, sir. It's visible. Visible.
So if
Fine.
you see this now, I have added the same values like 0.1 microfarad and 1.6K. You can see 90-degree phase shift is what we are getting. So it was about only the input frequency. Okay, so that is what we have done. And let's say if I change the frequency now. Oh, sorry. So even if I change the frequency, what is happening? That I am getting integration only, but the value is uh, very low. That the output is decreased. Okay, so on value for the value we have designed, the gain would be maximum. That is what we are trying to see here. So if I run an AC sweep now here, you see, one second. So let me just delete the phase part. P3 also we don't need. Okay, so this is our input, this green line, and our output is this. Okay, and this is maximum at what frequency? You can see roughly 200 hertz. Sorry, 150 hertz is what we are getting the maximum gain. Okay, that is a gain part. Then at 1 kilohertz, where is 1k? Yeah, here is 1k roughly. So it is in this part at 1k here. So if I run again, let's say around what frequency? Around 200. So as you can see right now, let me just select this. So if I go below this particular frequency, you can see that I'm getting, sorry, okay, so I'm still getting that only. And if I my gain is increasing. You see now the gain has started decreasing, and around 1k we saw that it was almost equal. Then after that it will start decreasing. So the frequency response, the bandwidth also we can check using AC sweep. So the gain is maximum around in this particular part, 100 to some 500, 600 range. Okay, so at 1k it is almost equal to our input. Okay. So anyway, we were just calculating. We just had to get the correct value in order for it to work. Other than that, it is working properly. Let us just give some other input now and see if it converts to our triangular wave or not. Still, we are not getting triangle here. We are getting spikes only. See?
You can change the now. You can try to change the R value, sir.
R value. Okay. So if I change the R value, no effect at all. I change, let's say this. This is also not giving much changes. So anyway, it might be some error from the supply end that we are missing. But yes, the integrator works this way only. Like we convert a sine to cosine. Yeah. Okay, so we are getting our sine and cosine. So this one is working. That other square wave part will check and I'll check and get back to you. Okay, so that might be because some supply error maybe. Okay, because the concept work this way. This is an ideal integrator. Okay, so any doubts on this? Okay, so if there are no doubts, we'll move toward, anyway, we tried a differentiator also. So differentiation would also be same if I apply on the sine wave, because sine's differentiation will again come as cos only. So our output will remain same. Okay, so let me just disconnect this. Okay, so this will, let me just put here. And this, let me just connect. Now this would be a differentiator. Okay, so if I run this, let me just, okay, some error. Uh, let us just leave this part right now. So anyway, let me delete this, okay, and so now the next thing that we have to check is our first order filter, first order low pass filter. So again, in this case also we will have a frequency. Either we can calculate the value and then apply it we had to do in the integrator part, or otherwise we can just put any circuit, and then for that circuit we can do the AC sweep and check what exact value it is coming out to be. Okay, so this is a circuit. Let me just implement this circuit quickly. So we will need, okay, let me take this one. Okay. Okay, so if you, like in this case, it is not written here which wire is which one. So you can look at here also. Okay, so this one is your plus Vs and this is minus Vs. Then this one is minus inverting terminal, this is non-inverting terminal and the output. Okay, so let us just use this and we will need one input and obviously some supply voltage. Okay, the same will be required here. Okay, then we will need ground. Okay, so same for this also. Okay, and we need some capacitors. One will be for feedback, one will be for this, and one more thing, a capacitor is what we need. Okay, so this is the component that we are going to need, and this is the circuit that we need to make RC. Now this is the RC which will basically be doing the low pass thing, and high pass because capacitor attract higher frequencies. It will basically ground all those higher frequency and it will pass our low frequencies to the op amp, which then can be amplified if we put in some amplification resistance and all, which are here you can see like this. Okay, so let us just quickly make this. So we will need three resistance. Okay, so this is one, and then we will take this. Sorry. Okay. So this is the component that will be doing our filtering part. Disconnect it here. Then this input will go to our positive edge here, and negative edge through resistance will be grounded, and it will have a feedback also from the output. One second. Let us just check if we are making the correct thing. Okay, yes we are. Okay, now so this part here will go to our this, and this is also going to be grounded. Then this is also going to ground. So this is also coming to ground, and this will be going. And this will be connected here, and this is the input that we will be giving here. Okay, now we need one load resistance also. Copy this one, put it here. So not copy. Okay, so this will be connected here. Okay, then this will be coming to ground. Okay, now our probes, this one will come here, and then this one will come here. Okay, so I guess we are okay. So if I run this now, so output is little damped. Let us just try to change the frequency. Okay. Okay. First, let us run AC sweep, which will help us figure out the low pass thing. Now, here you can see. Let me just delete the phase. So this is our output, and as you can see, it is passing these frequencies like till 25. Then after 25, it has started decreasing. So that is a low pass filter. So how we can now try to change it? Let me just decrease this resistance and see if it changes. You can see that it has the bandwidth has increased. Okay, so if I decrease this also, let's say, now what will happen? Again, the bandwidth still increases. Okay, because these are like both are inversely proportional to our bandwidth here, the frequency, cutoff frequency. Okay, so this is now we are going till roughly 6 kilohertz here. Okay, so around we can say, okay, 2.5, around after 2.5 it started decreasing and it is falling sharply, you can see. So let us just try that. Okay, so okay, so it is at, so we know at 2.5 it will be decrease. First let us just see normally how it is looking. Okay, so here you can see we have a gain also. Then the gain is here because we are using a non-inverting amplifier, and the gain factor is 2. Okay, so if I decrease this one, let's say to 500, in this case it would be 1.5. If I decrease it to 100, so now it would be almost, it should be same now. So anyway, uh, that was not our idea to look into it right now. So if I make it 1k, we have a gain factor of 2, so which you can see. Okay, now I will start increasing the frequency. So the gain is still okay. So we know around 2k, 2.5k, it should start coming down. So we are going easily around, now we are approaching 1k. 1k we have achieved, and still we have the same gain factor. Sorry. So now if I start increasing it again, now you can see that it has started decreasing a little. Now you can see it is coming down. Okay, so let me just set the time per division again. Okay, so if I start keep on increasing the frequency, so you see it is a low pass filter which is now dampening my output. Okay, so you can see it is almost zero now. Okay, so let me just show you like this. So you can see it is almost zero. So this is a low pass filter using first order low pass filter using op amp. Okay, any doubts in this?
No, sir.
Okay, so the next one we will do is a high pass filter, which is almost same, but there is only one change. This. So here we have we basically swap. We basically do this thing. Okay, so again this is inverting. Okay. Let me just there's one more thing I guess we can do. Okay, copy this. Uh, so let me just run AC sweep now. Okay, now you can see we are getting our high pass. So you can see that it is passing the higher frequencies here, and the lower frequencies are dampened. You can see here the frequency below zero are almost giving zero result. Then it starts increasing a little afterwards until roughly 6.3k, sorry, around 7.8 or 9 8k you can say. It would be less than our signal only, and then it is going beyond. Okay, so anyway, this sharp curve should not be there, but maybe we are missing some values. We can try to change that. Let me just see. Okay, so we are trying to increase the bandwidth here. I remember earlier we used to do this, like these two used to swap and make one high pass and low pass. But this one I was not expecting. Why this is falling down afterwards. So okay, let us just try this circuit. Okay, so these two are in series, and then this. Okay, so let me just select all, delete, take this. Two resistance is what we will be needing. One here, then one capacitor we will need. Okay, one input source. Okay, one ground connection for here. Then one ground connection for here. Then a DC supply. Okay, and again here also. I think we missed. Okay, we need to invert it. Okay. Then this will be grounded. Okay, and now we will need one more resistance for load. Okay, connect it here. Okay, so now let me give some probes. One here, another here. Okay, so let us just run the AC sweep first. Okay, so again, this is working as a band pass filter only. Like 63, and you see it, what we were trying to look is also getting here, but
Hello, sir.
yes, sir.
You take the frequency range up to 1 meg is more than enough, sir. Why? Because you design for 1K only, no,
I
sir.
know, sir. I know. No, I was
Uh,
just looking at the higher ranges also.
because
So
which we are using in the lab also, at the maximum get only 3 mega
yeah,
with
yeah,
the help
yeah.
of function generator.
Exactly, sir.
So
So
not going to
this
use it.
anyway we can take. I know that part.
Yeah,
So we
that's what
can
is
put
this
in
confusion.
maximum frequency as, let's say, mega also if we take.
1 mega is enough, sir. Okay.
So in this case it would act as a high pass only. Okay. What happened here?
Please run once again, sir.
Okay, anyway, 1 mega it will cut off somewhere around here, this point. Okay, so this anyway will act as our high pass circuit only. Okay, so we are at lower frequencies. Let us just try with small frequency of 1 hertz, let's say. What happened? Okay. Okay, so you can see we have output, but it is attenuated a lot because this is a high pass circuit and we are at 1 hertz. Okay, so if I start increasing, this input should start growing now. You can, sorry, output should start growing, which we can see. Okay, and let me just correct the scales again. Okay, so if I keep on increasing, the input value will keep on increasing again. Okay, so again, if I keep on increasing, okay, so now it is getting closer to the input value itself. Okay, so this one is a non-inverting amplifier, and both the values are like 1 and 1 here. So gain is minus of R2 over R1. So that is why this value will not go beyond it. So let's say if I make it 10, you see now this has increased. Let me correct the scales. Our input is 1 volt and we're getting almost 10 volts. So this is a non-inverting amplifier, we can see now. Okay, so if I start again, so you see it is almost constant till this particular point. So this is acting as a high pass here. Okay, so any doubt in this? So again, there is a band pass which is like this. This will basically pass one particular band only. So that we can calculate again with the similar formulas that we have. But there is one more, which is band stop, and this basically is done like this. This actually is a famous circuit, 20 active notch band stop filter. So this one we will try. Okay, so let me just go back, stop this, delete everything. Okay, so what we need here, let us just see once. So we will need three capacitor, three resistance, sorry, four resistance and op amp. Okay, so let me just gather three resistance, okay, one for load. Okay, then we will need three capacitor also. Okay, and then we will need one op amp. Let us just take this one here now. Okay, then one input supply we will need. One ground, one DC voltage, copy it and put it here. Okay, I guess that's it. So one will go here. Let us just make it 15, and this one is minus 15, and let us connect it like this. One second. First, let's make the notch, twin notch. So which would be like this. So two capacitor and one resistance in between. So let me just put all these things aside. Okay, so two capacitors. And rotate it. This has to be in middle here. Okay. So this one will be connected here. Okay, now we will need one ground for this. Okay, so this is one T we have made. Another T would be similar only, but instead of capacitance, we will have resistance and vice versa. So you see that resistance and capacitance, like opposite what we were doing earlier. Okay, so the another T let us make two capacitance, sorry, two in resistance. Okay, now connect it. Okay, now one capacitance. Let me just rotate it. Okay. One second, let me just put it bit this way so that we can see once it. Now this will be connected here. Okay, then this side is also getting connected. now our input signal will be given here. Yeah. And this will, let us just check, go to half here. Okay. And then what do we have? Minus is directly going as a feedback. Okay, so this is it. Then my load resistance, let me just place it this way. Now the ground connections. Okay, so this will come here and this will come here. Um, Second. Yeah. Okay, so now just we need to set our values. So anyway, let me just put the probes first. So this is our input probe, and this would be our output probe. So as per the circuit, C, C and R by 2, then R, R and 2C. So if I give it, let's say 1, 1, and this is 1, let's say 2K. So this one should be 1K, 1K, and this should be 2 microfarad. This is what this one
So
is.
capacitor grounded.
Yeah, yeah, yes, sir. That capacitor is also need to be grounded. Okay, so I guess that is it. Let us just run the AC sweep once, see if it is working fine. Okay. Uh, okay, even we can delete this. So it is going down. It is like stopping these this band. You can see like from almost 50 hertz to here this one, roughly 390 hertz. Let us just change the values and see if it makes any sense. Okay. So right now there is no feedback or amplification we have given. That is why the output is very little. So maybe we can try to add that also here. Just give me a minute. Okay, we will add some amplification also. This is working as a uh, non-inverting amplifier. So okay, let me just copy the resistance here. Put one resistance here, another resistance that will be connected here. and then from here to ground. So if I make it, let's say 4K, so R5 by R6 would be 4 plus 1, which will make it 5. So we should have a 5 as gain. So okay, now here you can see it is stopping this band. Okay, now if I change these values, let's say make it 100 nano this, then 100 nano this, then this would become 200 nano. Okay, so let us see what is happening here. Okay, let me just go back. We can see the different results that we want. Okay, and accordingly we can set our value. Obviously we are not calculating anything, so we have to rely on this AC circuit only. But anyway, what we wanted to see, the band pass thing, is what we are getting. Band stop, sorry, not band pass. This is a band stop. So you can see this is basically attenuating this particular band here from roughly 3 hertz to this point, which is like 39 hertz. So this part it is attenuating. Okay, so let me just make, let's say 10K. That would make these as 5K. I run the AC suite now. Okay, so you see it is. Okay, let me just. Okay, now what? Okay, so you can see here that we are getting a band stop curve here. Okay, so the band it is stopping is roughly, if I calculate, 3 hertz to 398. Okay, so let us just try that now and let's see. So accordingly, anyway, if we want for some particular frequency, we have to do the calculation, which we are not doing right now. Okay, what are we getting here? Okay, so there is some DC component added into our at what frequency? Okay, so the frequency is a lot here. Let me just make it, let's say 1 hertz. Okay, you can see that this is 1 hertz and we have some output, but it is almost zero. Let us just try to increase after. Okay, so 3 hertz anyway. We are in the band where we are stopping the signal. So after 390, we should start receiving some signal. Okay, you can see that right now we are at 100 hertz. Okay. 1 second. So we crossed it. We are getting, I guess, something here. Let us just try to expand. Okay, let me delete this. There is some DC component. Let me just add another capacitor to solve it. Okay, so you see that the capacitor has removed the DC part what you were getting. Okay, so where were we? So the part where we are. Okay, so we are still getting something random. This is also not properly working. What should be the issue in this? Okay, so let me just stop it once. So let me run the AC sweep again. So you see initial band is stopped. Then after 3 we are getting increment. And okay, now this one should be workable. Okay, so you see we are after that particular frequency, the band stop frequency, and here we can see that our signal is getting amplified. Okay, so anyway, let me decrease the frequency and move toward that band stop part. You can see it has stopped that. You can see that here. That it is stopping this part, and afterwards it increases again. Okay, so that was our band stop. So anyway, that calculation, exact calculation, you can do later on. Okay. So for today's assignment, I will give you this band pass filter. Okay, so you have to make a first order band pass filter using op-amp. This will be your assignment for day 4. If you have any doubts in this, just let me know. Otherwise, I guess we can stop for today.
Yes, sir.
Are there any doubts?
No doubt, sir.
Okay, so we can stop, I guess. Neha,
Yes,
ma'am?
we can wind up, sir, for today.
Sure.
Yes.
Okay, I guess Neha ma'am can take over now. Neha ma'am, are you there?
So madam is not here.
Yeah, I called her, so anyway, she's coming. Let me call. So now I guess we have completed our day for also. Now last day is left, which would be on embedded system design. Like we have embedded lab where we use microcontroller and some sensor interfacing along with it. So that part we will do tomorrow, and that we will do using a different platform. We will not be using Multisim Live there. We will be using Tinkercad. I'm sure most of you are aware about Tinkercad also.
So is it not properly? So not properly working in.
What?
Is it not properly working in a
Which
laptop?
one, sir? Which one?
Tinkercad. So it's somewhat difficult to load.
Tinkercad. So it is again online platform. So I doubt that would be any issue.
Oh, that will not be so. So maybe
Anyway,
our end may be slow. Our end may be slow. Network.
so it might be only the laptop problem, because generally what happens
Ah,
that these one of the benefit of using online simulators are like you won't be running anything on your laptop. So it's just a browser, and the simulation is running it at a very higher end system, which is at the company site. Okay, so we will anyway look at it. Anyway, I was also having some issues in this here today. uh, Maybe my system is getting a bit slow, or what.
yes,
So
yes,
something like that is the
yes,
only issue.
yes, yes. System speed is also a real problem.
Yeah, exactly, sir. So that
Yeah,
can be the only issue in this case.
network bandwidth is that's also problem.
Yes, sir.
So, participants, I have posted the link of session 2. You can update, mark your attendance there. And Devendra sir, thank you on behalf of Balwinder sir and Nitra Chandigarh. We'll be connecting tomorrow for the session now.
Thank you, ma'am. Yeah, we'll connect again at 10 tomorrow.
Yes.
And I have given the assignment for the day also.
Okay, sir.
Okay,
Okay,
sir.
thank you,
Thank
sir.
you, sir.
Okay, thank you, everyone. Bye.
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 Oh,
Thank you, participants. Just mark your attendance before you leave.
okay.
Yeah, sure, ma'am.